That means that x and ax have same direction. Okay, so what is the meaning of x and ax have same direction? X and ax are multiples of each other, right? They are linear multiples of each other. So x and ax are linear multiples of each other. Okay, so what we really are interested in, given a matrix A, what do we want to do? We want to see a linear transformation. We want to interpret A as a linear transformation first thing. And once we understand A as a linear transformation, then we know that every vector X is going to its image AX, right? And what are we trying to do? We are trying to see if there are any vectors, non-zero vectors, which upon action of A do not change the direction. Okay, so it might be possible that x always goes to a different direction. That is also possible, but sometimes it is possible that some certain spatial vectors will not change their direction even after action of a. Okay, that means that x and ax, they have same direction. In other words, x and ax are linear multiples of each other. If you find such an x, that x is spatial. Of course you want a non-zero x, because if you have x is equal to 0, then 0 will always get mapped to 0 under linear transformation, and there is nothing you can do about it, right? So that x is equal to 0 obviously is not a special vector. But if a non-zero vectors exhibit this property, then this type of vector is really very important, really very useful. So what we will call such a vector x, such a vector x in Rn. So I'm like specifically saying x not equal to 0 is called as an eigenvector. And x and x are in the same direction, right? They are multiples of each other. Then we will write ax is equal to lambda times x, right? So ax, the image of x is lambda times x, where lambda, that scalar multiple is called as eigenvalue, right? So how much is the change in length? We are only interested in keeping the same direction. So I'm underlying this same direction here, because direction means that the one dimensional subspace spanned by x, right? So direction is not to be taken in the sense of like the direction that we see. It might change the direction in the sense that if the lambda is negative, then you will go in the opposite direction, but still it will lie in that one dimensional subspace spanned by x, right? So that is what we really want. Okay, so change the direction, do not change the direction. So basically that's why I have underlined it. The meaning is that it should lie in that one dimensional subspace. Okay, eigenvalue called as eigenvalue corresponding to lambda. Okay, corresponding to x, the eigenvector x. So this is what we have, eigenvalues and eigenvectors. So more formally, like this is the geometrical and intuitive reason why eigenvalue and eigenvectors are defined. Excuse me, they are defined in this way. So like more formally, how do we define? So given A in Rn by n, if there exists lambda in so lambda in R or C, will come to that. So if there exists a vector x not equal to 0 in Rn, such that Ax is equal to lambda x for some lambda, then x is called as an eigenvector and lambda is its corresponding eigenvalue. Okay. So what you look at, basically what you focus is this equation, right? Ax is equal to lambda x, x is not equal to 0. So you can have a minus lambda I x is equal to 0. These two are equivalent. I'm just rearranging the terms. So these are equivalent. And now a minus lambda I is a matrix in n by n, right? For some value of lambda. So note a minus lambda I is a matrix in Rn by n for some value of lambda, correct? So if this matrix is not full rank, right now you have a minus lambda I, so you will start picking up values of lambda. And if you find out for certain value of lambda, if this matrix is not full rank, what does that mean? That means that it has some non-trivial element, non-trivial meaning non-zero element in the null space of a minus lambda I. And that will satisfy ax is equal to lambda x. So what we are really interested in is this particular matrix and the null space of this particular matrix for every real number lambda. So wherever, if you are able to find out a lambda, if you are able to find out a lambda such that a minus lambda I has a non-trivial null space, a minus lambda I has a non-trivial null space, then you have found out corresponding eigenvector also, right? If the matrix a minus lambda I for some value of lambda is invertible, that means that for that particular lambda, you see that a minus lambda I will have full rank, or it will be invertible matrix because it's a square matrix. And that implies that x has to be equal to 0. So you cannot find out a non-zero vector x in this particular case, right? So what will we do? So this is x in.
Hello.
Yes.
I have one doubt. Like in x equal to lambda x not equal to 0. Let's say x belongs to null space of A. Like there exists a non-trivial vector x, which is not equal to 0 and belongs to null space of A, and lambda equal to 0. Then will that combination be eigenvalue eigenvector?
Yeah.
0 comma x belongs to null space of A.
Okay. Yeah, that will be a combination, eigenvalue eigenvector combination. That's right.
Thanks.
So there is x in Rn, x is not equal to 0. So what do we do? So we will find lambda in R such that a minus lambda I is not invertible, or a minus lambda I is not full rank. They are same, right? Because that will mean that for this lambda, there exists x not equal to 0 in the null space of a minus lambda I, right? So there exists x not equal to 0 in the null space of a minus lambda. That is what will happen, right? And then what does that mean? For that particular lambda, a minus lambda I x is equal to 0, which means that ax is equal to lambda x, which means that lambda and x is an eigenvalue eigenvector pair, right? We'll call this as an eigenpair also. Okay, so it is an eigenpair. Lambda and x is an eigenpair. That is what we have. Okay, so now one thing to be noticed here is that a minus lambda I is not invertible. So you have to find out lambda, right? You have to find out lambda such that this is going to happen. But a minus lambda is not invertible is same as saying determinant of a minus lambda I is equal to 0. because the matrix is invertible if and only if determinant is not equal to 0. That means that the matrix is not invertible if and only if determinant is equal to 0. So I'm finding out lambda says that this is not invertible. This is true if and only if determinant of a minus lambda is equal to 0. So now, if you construct this determinant of a minus lambda I equated to 0, what would really happen? What would really happen is that you will have an equation in unknown lambda. And if you can solve that equation in lambda, which is there, then what will happen? You will be able to find out all possible lambdas for which a minus lambda is 0. You don't have to put one by one lambda values for entire real numbers. This will be an easy trick to compute determinant of a minus lambda. With this, can anybody tell me what will this equation in lambda really will look like? Determinant of a minus lambda. What will this equation really will look like?
Polynomial.
Yes, it will be a polynomial in lambda. What will be the degree of that polynomial?
N.
Degree of that polynomial will be n. And what will be the lambdas of our interest? What will be the eigenvalues?
The roots of the equation equal to 0.
The roots of that polynomial, determinant of a minus lambda equal to 0. The roots of that polynomial will be the eigenvalues. But now, will the roots be always real? Is it possible that the roots are always real? You know roots of a polynomial, they can be complex as well, right?
Yes, sir.
Yes, sir.
So how do we proceed then if you have complex roots there? So never mind, if the roots are complex, that's fine. So the thing is that you started with the scalars, okay? The scalars that we started with in all this discussion, the scalars were in R, right? The scalars, the field of scalars was R, right? The matrix A was containing elements from real field, right? R n by n. So entries of the matrices were in R. So what happened, you had this particular thing that you thought that okay, this geometrical interpretation of not changing the direction and all, this will be what will be really important for me, and then this scalar obviously in this interpretation becomes a real scalar. But it is not necessary that this determinant of a minus lambda I equal to 0 will have real roots only, right? So if the roots are not real, so the problem with this is that the field of real numbers is not kind of complete field. That means that all the polynomial equations with real coefficients do not have real roots only, right? So that property holds true for only complex field. That means that if you have a polynomial with complex coefficients, then all the roots will be complex. So that field is kind of complete, right? So that is the problem, right? So you don't have complete field, real field. So it is going to happen. So eigenvalues can be imaginary. So corresponding to imaginary eigenvalues, you can have complex eigenvectors. But then the question is, where are you seeking your eigenvalues and eigenvectors in? If you're seeking your eigenvalues and eigenvectors only over the field R, then we'll say that eigenvectors do not exist. If you're seeking them over Cn, the complex field, then you know this interpretation also does not make much sense. You just say that it's an invariant space. Okay, so right now we don't worry about complex eigenvalues and complex eigenvectors. Complex eigenvectors is something that we will not think of. Okay, so we'll say eigenvalues will be real or complex based on the roots of this determinant polynomial, and corresponding to real roots of this determinant polynomial, you will compute what are the eigenvectors. They definitely will be real. Corresponding to the complex eigenvalues will not do anything. We'll say that eigenvectors do not exist. for those eigenvalues. Okay, so if you go to Cn, so vector space over the complex field, then this problem will not arise. But for real field, this problem arises. Okay, so I hope this part is clear. Is that okay? Is that okay? So let us take few examples. So let us take this simple example 2, 1, 1, 2. So can you tell what are the eigenvalues and eigenvectors of this? So the simpler thing would be rather than start looking for eigenvectors like vectors x which are invariant and so on and so forth. What we can do is we can look at this particular trick. So determinant of S minus lambda I is what you will compute. So determinant of this S is 2, 1, 1, 2 minus lambda I matrix is lambda 0, 0, lambda. And you have to look at determinant of this matrix, right? So what is this? So determinant of 2 minus lambda 1, 1, 2 minus lambda is equal to 0. That is the equation that you are looking at. And what is the determinant? 2 minus lambda whole square minus 1 is equal to 0. So 2 minus lambda square minus 1 equal to 0. I think you can do this 2 minus lambda minus 1, 2 minus lambda plus 1 equal to 0. So what will be the eigenvalues? Lambda is equal to 3 and lambda is equal to 1. Is that right? So lambda is equal to 1 and 3 are the eigenvalues, right? And how do you find out corresponding eigenvectors? S minus lambda I you construct. Okay, so S minus lambda, if you take 1 times I, meaning that the matrix becomes 2, 1, 1, 2 minus 1, 0, 0, 1. Right. So what is this matrix? This matrix is 1, 1, 1, 1. Correct. So this is the matrix that you get, and then you have to look at the null space, right? So you have to look at the null space. So you have to find out a vector x such that it's in the null space of this particular, right? So let x corresponding to lambda equal to 1. So I think I can take 1 minus 1 as the vector. If I take 1 minus 1 as the vector, then what happens? Do you all see that Sx is equal to x? So x is the eigenvector corresponding to the eigenvalue lambda is equal to 1. And similarly, is this the eigenvector? Can you just check? Is this okay?
Yes.
That's what is happening. But if I take y to be equal to 2 minus 2 in this particular case, then will y be an eigenvector corresponding to the eigenvalue lambda equal to 1?
Sir, can you just repeat?
If I take y is equal to 2 minus 2, the vector y is 2 minus 2, then is y an eigenvector corresponding to the eigenvalue lambda is equal to 1?
Yes, sir.
So
Sir,
in fact, if I take any vector z to be equal to alpha minus alpha for alpha not equal to 0 real number, then this z will always be an eigenvector corresponding to the eigenvalue 1.
Yes, sir.
Is this surprising? Is this surprising? It's not surprising, right? Why is it not surprising? Because what you are looking at S minus lambda I and null space of S minus lambda, right? So this is set of all vectors in Rn such that S minus lambda I x is equal to 0. So this is a subspace. So for every vector x in null space of this S minus lambda I, for every, I'll just make sure every vector, every non-zero vector. Okay, I'll make it precise, every non-zero, because this is a subspace, zero vector is also there. So for every non-zero vector x belonging to this, what is the property? S minus lambda I x is equal to 0. That means that Sx is equal to lambda x. So this is the very relation which defines this subspace, right? So every element in this subspace, every vectors in this subspace is going to satisfy this. So once you find one vector, any scalar multiple of that vector, which is how basically you are building this null space of A, is going to be the eigenvector, right? So eigenvector is not unique. So typically what we will do, so in this null space direction, S minus lambda I, what we will do, we will like to find out basis, right? So we'll choose orthogonal basis of this subspace. So we'll, in this particular case, what is the dimension? So in this particular case, you see dimension of S minus lambda I is equal to 1, right? For lambda is equal to 1 and 3. For both the eigenvalues, you will get two subspaces. Lambda equal to 1, you will get one subspace. Lambda equal to 3, you will get one subspace. Then what will happen? You'll have two different subspaces of R2. So these are subspaces of R2, you have to understand. And these subspaces of R2 are something that we'll get, right? So the interesting thing to look at is that this is your R2. Okay, this is your R2.
Sir, is it the dimensions of null space of this?
Dimension of null space. Yeah, you're right. Dimension of null space of this. So if you look at this R2, then basically what is happening? So geometrically, what is happening? So this is your R2. Okay. There are various vectors in R2. So the vectors of importance to us are, let us say 1, 1 and 1 minus 1, right? So these are the vectors that are important to us. And then there are two other vectors, let us say E1, which is 1, 0 and 0 minus 1. Okay, so these are the vectors that you have here. Now what is happening? You are having action of the matrix A on this entire R2 space. Then what happens? Where does this vector E1 go to? Can anybody tell? Where does this vector E1 go to? This is E1, this is E2. What is AE1? AE1 is the first column of the matrix, right? So it goes to 2, 1. So where is 2, 1? So this is 1, 2, 1. So E1 goes here, right? E1 goes here. Where does E2 go to? It goes to 1, 2, right? So 1, 2. So this is where E2 goes to, right? So this is AE1, this is AE2, right? But what happens to 1, 1? What happens to 1, 1? 1, 1 still remains 1, 1. Correct, and minus 1, 1, 1 minus 1 also remains still 1 minus 1, right? So these are the vectors that do not change the direction. So basically every vector on this line and every vector on this line do not change the direction, right? So these vectors, basically that means this subspace. So this is the subspace that we are really talking of. So this subspace, so one subspace, so this is a subspace corresponding to this S minus, so 1, 1 was eigenvector with 3, right? So S minus 3 lambda, S minus 3 times identity. So this is one subspace that you get, S minus 3, null space of this. And this is another subspace, S minus identity. Right, so these are the two subspaces in R2, and the interesting thing to note here is that these subspaces are orthogonal to each other, right? So these subspaces are orthogonal to each other here. That's the interesting thing to look. Both the eigenvalues were also real in this particular case. Okay, so this is interesting thing. So let us see that. Let us note that. So is this picture clear, geometry clear? So you see this subspace x-axis is actually going to this subspace, right?
The second eigenvector will be like 1 and like 2 comma 1, not 1 1. Like 1 is minus 1 1 and the other will be 2 1.
No, I
No,
have
sir, it'll be
1 1 and 1 minus 1.
Yes, sir.
1 1 and 1 minus 1. That is what I have.
Yes, sir.
Okay, so here I have drawn 1 1 and minus 1 1, but it doesn't matter. Minus 1 1 is same as 1 minus 1. It's just minus 1 times, right? So ideally, when I draw the figure, I should. So this is not the eigenvector. The one that you told me, the eigenvector that you told me was this. Correct? So this was the this is 1 1. This is 1 1. And this is 1 minus 1. So these are the eigenvectors that you had told me. So I had computed minus 1 1. So I drew it the other way around. But it doesn't matter. The null space is basically the same. Is that okay? So this is the diagram. This is what is happening. So these vectors, so there are certain vectors which are not changing the directions. They are, so to speak, invariant, right? Under the map S, under the linear transformation S, they are kind of invariant. Okay, so this is something that is interesting to know. Okay, so this is one example. Let us take another example. So the example that we take is Q, which is of which is of the 0, minus 1, 1, 0. Okay, so this is a rotator matrix, if you remember. This matrix is a rotator matrix. So will this matrix have any eigenvectors? Before even going to compute anything, can you just think of geometrically what is this matrix doing? Will there be any eigenvectors?
Sir, no, because it's rotating.
Correct. So because this matrix is rotating every vector, no vector x is fixed under the action of Q, right? You pick any vector x, it will be rotating. So it will be rotating in like what? How much? Minus 90. It will be rotating in 90 degrees, right? So that's what will happen. So there is no eigenvector. So what do you suspect here? What do you suspect here is probably what is going to happen? The eigenvalues. What will happen to eigenvalues now? Imaginary. So let us see Q minus lambda I. So what will be this? This will be determinant of Q minus lambda. So I'll just directly write this down. Is that right? Which means you have lambda square plus 1 equal to 0, which means that lambda is equal to plus minus I, where I is square root of minus 1 basically. Some people write it as J, so I'm just making sure that in maths we write I. In electrical engineering, electronics, like those people have like J omega, right? E power minus J omega, that's what they think. So clear. So the eigenvalues are imaginary and eigenvectors do not exist. Okay, so that is what is happening. So similarly, now only through geometry you tell me. So suppose this is the space R2 and this is y is equal to x subspace. Okay, this is y is equal to x subspace. Okay, it's passing through origin. And I have a matrix Q. I have a matrix Q which is giving me reflection through this y is equal to x line. So reflector matrix, right? Like rotator matrix, we had reflector matrix also. So we had defined what is a reflector matrix. So can you tell me what are the eigenvalues and eigenvectors of this reflector matrix? So I want everything. Like, can you tell me what is the reflector matrix Q here? And what are the eigenvalues and eigenvectors of this reflector matrix? So first tell me what are the eigenvalues and eigenvectors of this reflector matrix? Geometrically you tell.
Sir, it'll be the same line. y is equal to x, that will be the space, which is the eigenspace.
Corresponding to which eigenvalue?
Corresponding to 1.
Eigenvalue 1. Why? Because every vector in here, so you pick any vector here, non-zero vector. So suppose I pick this vector, which is 1, 1. Then under the action of this reflector matrix, 1, 1 is going to go to 1, 1, right? Every vector on this line y is equal to x is going to be the vector on the line y is equal to x. So 1, 1 is one eigenvector. Eigenvalue is 1 because it is going to itself. So eigenvalue is 1, eigenvector is 1, 1. Okay, that is 1. So 1 and 1, 1. That is one eigenvalue eigenvector pair, right? What is another eigenvalue eigenvector pair?
Sir, -1. When it's 90 degrees to y is equal to x, the line.
Correct. So what happens if you have this vector -1, 1? Then what happens to this vector? This -1 vector goes to 1 -1 vector, right? So every vector, so if you look at the orthogonal, so this line if you take, so this line is y is equal to -x basically, y is equal to -x line. What is happening in this line? In this line, every vector you take, under the action of q, it is becoming its negative, right? You remember that's how we actually constructed this Q matrix. You remember the construction of Q. You first chose the vector in the direction of the subspace y is equal to x. You said that your Q should be such that Qx, so QV should be equal to V and QU should be equal to -U. That's how you constructed the matrix Q. Do you all remember this? The way we constructed this matrix Q, the reflection matrix Q, actually is through its eigenvalues and eigenvectors. So what is the other pair? The other pair is lambda is equal to -1 and the eigenvector is -1, 1, right? So again, you see this matrix Q. So you construct this matrix Q and tell me what are the entries of this matrix Q. But the interesting thing here is that you have again two real eigenvalues and corresponding eigenvectors. And once again, the eigenvectors, the spaces, null spaces are actually orthogonal to each other. Okay, so that is what you have. So in general, it is not necessary that the eigenspaces, that null spaces are orthogonal to each other. In general, it is not necessary, but here, like in these two examples that we took, this thing really happened. So is this clear geometrically what is really happening and what we are trying to get at? Is that okay? So one more example we'll take. So take matrix A to be equal to 8, 3, 2, 7. Okay. So these are the examples which I'm taking from Gilbert's book actually, because then I have calculations readily done with me. Okay. So now for this matrix, can you tell me what are eigenvalues and eigenvectors? So determinant of A minus lambda I is what you have to look at. So determinant of 8 minus lambda 3, 2, 7 minus lambda, right? So this is what you have. So if you expand this, what will you get? 8 minus lambda, 7 minus lambda, minus 3 minus r. So you'll have this polynomial lambda square minus 15 lambda plus 50, right? And which means that lambda minus 10, lambda minus 5 is equal to 0, which means that lambda is equal to 5 and 10. These are the eigenvalues. So these are real eigenvalues. And what are the eigenvectors corresponding to these eigenvalues? What is the eigenvector? Correct. So if you plot these on xy plane, then the one eigenvector is basically this 1 minus 1. And the other eigenvector is 1, 2, 3. Right? So this is another eigenvector. So clearly these are not orthogonal to each other. So basically this is the eigenspace you are looking at for one eigenvector, and this is the eigenspace you are looking for the another eigenvector, right? So these are not orthogonal, obviously. So it is not necessary that every time you get orthogonal eigenvectors, right? So this is something that I just wanted to say. Is that okay? Okay, so let's go to one more example. Let us take A to be equal to 1, 1, 0, 1. Okay. Can you tell me what are the eigenvalues and eigenvectors?
One comma one.
So eigenvalues are 1, 1, right? What are the eigenvectors? So you look at the null space of, so A minus lambda I, right? So A minus I is basically 0, 1, 0, 0, and you want to have that x1, x2 is equal to 0, 0. So what does that mean? What do you get your eigenvector x as?
1, 0.
1, 0. And that's it. There is only one eigenvector corresponding to these eigenvalues 1, 1. Right? So now this matrix, like in the previous cases so far, what were you observing? You are observing that you are getting two null spaces, right? Two eigenvectors. So this eigenvector and this eigenvector, they were kind of linearly independent, right? And then you are getting two null spaces n1 and n2 corresponding to this. But here you are getting only one null space, right? Which is basically the x-axis 1, 0. This is the null space you are getting, and that's it. So can you sense something different has happened in this particular example? Do you see that something different has happened in this
Multiplicity
example?
of the
Both
roots.
eigenvalues are same.
Yeah, correct. So multiplicity of roots, something has happened, and that multiplicity of roots has created some problem. But it is not always necessary that multiplicity of roots should create a problem. You take A to be equal to 1, 0, 0, 1 identity matrix. What are the eigenvalues? What are the eigenvalues?
So 1, 1.
Correct. 1, 1 are the eigenvalues. So lambda 1 is equal to 1. Lambda 2 is also equal to 1. Exactly like in this case, you had two eigenvalues. Both of them were same, 1, 1. But corresponding to lambda 1, what is the eigenvector? Can I take E1? And corresponding to lambda 2, I can take E2. So if you see here, one space is spanned by this vector E1, 1, 0. The other space is spanned by the E2. Right. So again, in this particular case, even if the eigenvalues are repeated, you get two independent eigenvectors, right? In this particular case, you got two eigenvalues which were repeated, but you got only one eigenvector which was linearly independent. Here you still got two eigenvectors which were linearly independent, right? So something is happening. Okay, something is happening. So this is what we want to investigate. What is happening? Some cases you got eigenvalues to be real, but the eigenvectors were not orthogonal. Some cases you did not get any eigenvalues. Some cases you got eigenvalues real and eigenvectors were orthogonal to each other. Right? So all these different things are happening. So what are all these different things, and why these things are happening? So this is something that we want to investigate. But through these examples, do you understand the geometry? Do you understand what is really happening here?
Sir,
Yes.
I did not understand, like you like just chose E1 and E2, right? Because every direction is going to be kind of an
No. Can you
eigenvector
say?
direction.
No. Can you say it again?
So like how did you arrive at E1 and E2 to be the eigenvectors of identity matrix?
Okay, so lambda I minus, sorry, what A minus lambda I, right? That is what I have. A minus lambda I, right? That is what I want. So A minus lambda I is basically zero matrix. You agree? Correct?
Yes, sir.
So what I wanted to start with, I wanted to start with the null space of this matrix, right? So I am looking at null space of this matrix. That is what I'm looking at.
Yes, sir.
So the null space of this matrix is two-dimensional null space. So far, we had only gotten one-dimensional null space. Now we have gotten two-dimensional null space. So in two-dimensional null space, what am I going to do? I'm going to choose an orthogonal basis for this subspace. So I chose E1 and E2. Okay.
Okay.
That's
Yes,
the
sir.
start.
That was
It is
my
not,
doubt. Like,
yeah,
you have
it is
just
not
chosen it.
necessary. I will choose any other. So I can choose this also. So this is a basis of entire R2.
Yes.
Because I want to choose orthogonal basis. If I decide not to choose orthogonal basis, then I could have chosen these two vectors also, right? So these two vectors are also basis. So basically any non-zero vector you pick in R2, that will be an eigenvector. Okay. So that is
Right.
what you are. Yeah. Okay. Dipayan, do you have any doubt, Dipayan? Okay, thank you. So this is what we have. Okay, so there are several observations. So let us write those observations down. Okay, so let us write those observations down. So what are the observations that we have? So the first observation is the following. So trace of the matrix A is actually the sum. Trace of matrix A is actually sum of diagonal entries. Okay. Can you check that this trace is actually equal to lambda 1 plus lambda 2, which is sum of eigenvalues also? Can you check that? In all the examples that we had done, is that true? Go back to each and every example and see it's indeed the case. 1 plus 1, 2, 1 plus 1, 2, right?
Yes,
1 plus 1, 2, 1 plus 1, 2. Everywhere you go, 8 plus 7, 15, 10 plus 5, 15. Everywhere. 0 plus I minus I, 0. Right? So this matrix, you did not tell me what is the answer, what is the construction. Otherwise, I could have done for this also. Similarly, in this matrix also, 2 plus 2, 4, 3 plus 1, 4, right? So all the examples that we have seen, trace is actually equal to sum of eigenvalues. Similarly, determinant of A is product of eigenvalues lambda 1, lambda 2. Can you check this also? Can you check this also?
Yes, sir.
In all examples, it is true. You tell me, why is this true? Why do you think is this true? Can you tell me why is this true?
Sir, when we do A minus lambda I, in all the diagonal entries, when we multiply the constant, that will be the last term, and all the other terms will have some lambda.
So you are looking at determinant of A minus lambda I equal to 0. That's the polynomial you're looking. Okay, so all the examples that we had, it was a quadratic polynomial, right? This was a quadratic polynomial. Do you all agree? In this particular case, at least. 2 by 2
Yes,
case. Yeah. And in this 2 by 2 case, this is the quadratic polynomial. So suppose lambda 1 and lambda 2 are actually the roots of this polynomial. How will you construct this polynomial back? How will you construct this polynomial back? What will be this polynomial determinant of a minus lambda I?
So lambda 1 times lambda 2 will be the, like if we write down the polynomial as a lambda square plus b lambda plus c.
So we don't have a lambda because we
Yes,
have a monic polynomial here, right? So we don't have
right,
a
sir.
lambda. So we have lambda square plus a lambda plus b is equal to 0. Yeah. So this is a lambda square plus a lambda plus b is equal to 0. Then what will be a and b here?
So lambda 1 times lambda 2 will be b, and lambda 1 plus lambda 2 will be minus a.
Correct. So now you use this and compare it with actual expansion of determinant of a minus lambda I, and then you will see that these properties are natural. They need to be satisfied, right? So you just do one more step, one more calculation, like Aditya was saying, and then once you do that, you will understand that this is what is really going to happen. Okay, so that's the reason. That's the reason. It's a monic polynomial. Because it's a monic polynomial, you will always be uniquely having this thing. And now if we go further in a 3x3, 4x4 matrix, then what I know for sure is that lambda to the n minus 1 coefficient and the constant coefficient, they still will be trace and determinant, isn't it? The other coefficients will be different, but these coefficients, like they will be like, so you have lambda 1 plus lambda 2 plus lambda n as your first coefficient. Then you will have lambda 1, lambda 2 plus lambda 2, lambda 3 plus lambda 1, lambda 3, and so on and so forth. All two products, all three products, and the last term will be all n products, lambda 1, lambda 2, lambda n, the roots, right? That's how you can generate the polynomial with plus minus alternating sign, right? That's what you will have. So you can see two important functions, trace and determinant. You can relate with the eigenvalues and eigenvectors. So somebody initially was asking, like, if there is a non-trivial null space, then what happens? Do we have like eigenvalue, eigenvector? So if you have a non-trivial null space, so lambda equal to 0 is one eigenvalue, and you see that determinant of A is also equal to 0, right? So that eigenvalue eigenvector relationship, from here you can see what will happen. So look at the trace of the matrix, then the second value is automatically known. You don't really need to compute eigenvalues that way. So these are few properties that you can use to compute eigenvalues and eigenvectors. So this is something that I had to say, and one of the important things that you notice here is the following. Okay, so typically now we all agree that given a matrix A in Rn by n, okay, given a matrix A in Rn by n, if you want to compute eigenvalues, what you will do is determinant of A minus lambda I equal to 0. That's what you will compute. So you'll get a polynomial, get a monic polynomial of degree n. Is that okay? You will get a monic polynomial of degree n, then compute the roots. Compute the roots of this polynomial. And once you compute the roots of the polynomial, what do? Compute the corresponding null spaces. Compute the corresponding eigenvectors, right? That is what you will do. So this is something that you will do. So now you tell me practically, when we are solving this problem, where all we will get into trouble. So how much is the computation of determinant of A minus lambda equal to 0 for a matrix n by n? Is computation of determinant an easy task computationally? How many computations will require? So basically you have to go through all the permutations, right? So you have to go through all n factorial permutations of the entries in the matrix, right? So that's how you will expand the determinant. So typically it will be really very like tedious computation, so to speak, because if you have a matrix of the size n by n, then you have to go through lots of expansion terms. Okay, so this part is difficult computationally, but at least doable. Then you will get what? You will get a polynomial of degree n, right? So you'll get a polynomial of degree n. How will you compute roots of this polynomial? Is the computation of roots of this polynomial easy task or difficult task? Anybody? How will you compute the roots of this polynomial?
In cubic, it is doable, but beyond that, I don't think there's any analytical method.
So we can use numerical methods to find the roots.
Yeah, so what Aviraj is saying is that up to degree 3, but up to degree 4 also, like square of quadratic, up to degree 4 you can do it by formula, but beyond degree 5 you cannot do it by formula, right? So Aviraj, do you know the reason why?
No, sir.
No? You did algebra course, no? Modern algebra?
Achha, yes, sir. Yes, sir.
Yeah, in that course you did not see why this is the case.
We did a proof. I remember, but I forgot.
Okay, so mathematically it is a proven fact. Okay, so sometime I'll tell a very interesting story about who proved this and how these things actually turn out. But beyond degree 5, there is no formula involving that radical sense. Like for quadratic, you have this minus b plus minus root b square minus 4ac by 2 and so on and so forth, right? For cubic also you can have formula, but beyond that you do not have formula. Beyond degree 5 you do not have formula to compute roots, right? So computing roots using formula is out of question. Then Aditya is saying use numerical methods. So what type of numerical methods will you use, Aditya? Aditya?
Yes, sir. We can like we learned in these like I don't remember the names, but like,
yeah, but like bisection method,
Expert
regular false
bisection
method.
method
These
and
are the
all
type
this.
of things you're saying, right?
Yes,
But
sir.
how many roots you get by that method? If you start with a bisection method, how many roots you will get?
We'll get one root.
You'll get one root. Is that root exact root or approximate root?
Approximate.
So first you will get one root. So if I am understanding you correctly, you will say that you apply Newton's method, like whatever method you know, you get one root. You divide the polynomial by that factor, then you'll get a degree n minus 1 polynomial and keep on doing this. Is that what you are saying?
Yes, sir. That could be one approach.
Yeah, but you will not get exact roots. So division is not possible. Then there is a problem, right?
Yes.
So
sir.
ever wondered how the roots of polynomial are computed? So you use this like in a software you go today, any software you like want to see, any software you want to see. There is a command always in that software to compute roots of the polynomial, right? So once you type that command, so in MATLAB, for example, the command is roots. So you give the command roots and the argument to this function is the coefficients of the polynomial. You will get all the roots listed in a fraction of second, right? This bisection method, regular falsy, they have convergence issue also. So anybody knows how these roots are actually calculated? No. So you will be surprised. Okay, tomorrow I'll tell you how these roots are calculated. In the meantime, you also try to find out on your own what happens. What is the algorithm that compute roots of the polynomial? Okay, but if you are able to find out the roots of the polynomial, it turns out that you will be able to find out eigenvalues easily, right? But you please appreciate one thing today before we end the class is that computation of eigenvalues, please appreciate it's not an easy problem. Okay, it is extremely challenging. It's not an easy problem, as easy as it looks like. Unfortunately, in all your courses so far, what you have done is only 2 by 2 matrices, 3 by 3 matrices, determinant of A minus lambda equal to 0, job done, right? That's all you have done. So beyond that, you have not gone. In real life, you will not have 2 by 2, 3 by 3. You will have a case where you have like 20 attributes. So you will have a 20 by 20 matrix at least, right? Covariance matrix is of such 20 by 20 whose eigenvalues you are interested in. So you end up with degree of 20 polynomial. So what will you do in real life? That is not possible. So how do you compute eigenvalues in real life? That's a very important question. Okay, think about it. Think about how those softwares numerically compute roots of the polynomial. You just think about it. If you get the answer, you tell me tomorrow. Okay. So I think that's it today. We have overshot the time. So let us stop here. We'll continue this discussion tomorrow. Okay.